Am I audible?
Yes, ma'am.
Okay, just I am taking your attendance. After that, I will call only the absent roll numbers. I am calling only the absent roll numbers. AMB 25. AMB 25. CB 78. CB 78. CB 80. CB 80. Civil Engineering 80. Civil Engineering 91. 91. CB 91. 92. 93. 94. CB 94. CB 94. CSB 61. Computer Science 61. Computer Science 61. Computer Science 63. 63. Computer Science 63. Electrical Engineering 55. Electrical Engineering 55. 55. Electrical Engineering 55. 56. 56. Electronics 41. ETB 41. ITB 56. Information Technology 56. Information Technology 56. IT 59. Information Technology 59.
Present, ma'am. Present, ma'am.
Okay, okay, okay. Mechanical Engineering 49. Mechanical Engineering 49. 51. MEB 51. Metallurgy 30. MMB 30. Mining 25. Mining 25. Mining 26. Mining 26. Yes, only these students are absent. The roll numbers, I have already called the absent roll numbers. Those students are now absent. Now I will start my topic. Is it visible? Is it
Yes, ma'am.
visible?
Yes, ma'am.
Yes, ma'am.
Okay, okay. Today I will start a new chapter, solution in series. Okay. Here you see this is an effective method when the differential ordinary linear differential equations, when we consider ordinary linear differential equations with variable coefficients, you see variable coefficients, okay, and order greater than 1, then this method will be effective. Most effective method of solution is based upon the use of power series. Okay, here you see we have to consider ordinary linear differential equations with variable coefficients and of order greater than 1. In this case, this method of solution based upon the use of power series will be effective. We first define ordinary point and then we will define singular point and a special type of singular point which is called regular singular point. We consider this differential equation, you see, where you see the coefficients P0x, P1x, Pnx, all these are polynomials in x. P0x is a polynomial in x. That means this is a variable coefficient. All this P1x, P2x, Pnx, all these are polynomials in x. And also Rx is a polynomial in x. Now, if at some point P0x is not equal to 0, suppose we consider x equals to x0, where P0x is not equal to 0 at this point x equals to x0. Then this point x0 is called an ordinary point of this differential equation. So this point x0 will be called an ordinary point provided this coefficient is not equal to 0 at that point. This coefficient, what is this implication? Which is actually the coefficient of highest order derivative involved in the differential equation. Since the highest order derivative here in this differential equation is nth order, you see, and the coefficient of this highest order derivative is P0x. If this coefficient becomes non-zero at some point x equals to x0, then it is called an ordinary point. On the other hand, if this coefficient becomes 0, then it is called a singular point. Suppose at x equals to x1, this coefficient, which is the coefficient of highest order derivative involved in this differential equation, suppose P0x, here the coefficient of highest order derivative, if P0x becomes 0 at x equals to x1, like this, then we say, just you see, P0x1 equals to 0, P0x1 equals to 0, then we say x1 is a singular point. And a point which is not a singular point is called an ordinary point. Okay, if a point is not a singular point, then it is called an ordinary point.
बंद करो.
Just a minute. Just a minute, please. Am I audible?
Yes, ma'am.
Is it visible?
Yes, ma'am.
Yes, ma'am.
Okay, due to some emergency call, I have actually received the call. Sorry for interruption. Okay, just I was talking about this ordinary point and singular point, right? Ordinary point means the coefficient P0x, which is actually the coefficient of highest order derivative, and this coefficient becomes non-zero at an ordinary point. And if it becomes zero at some point, say x equals to x1, then it is called x0. You see, at x equals to x1, if this coefficient becomes zero, then x1 will be called a singular point. And in this case, you see x0, which is called an ordinary point of the differential equation, provided P0 is not equal to 0 at the point x equals to x0. Is it clear? At an ordinary point, this coefficient becomes non-zero, and at a singular point, this coefficient becomes 0. Is it clear to all of you?
Yes, ma'am.
Yes,
Okay,
ma'am.
now I proceed. Okay. Now you see, regular singular point, what is it? You see, just take an example, then it will be better to understand. You see, this coefficient, which is the coefficient of highest order derivative, this coefficient becomes 0 at the points x equals to 1 and x equals to minus 1. So this x equals to 1 and minus 1, this will be called singular points, right? Because this coefficient becomes 0. But here you see, but if we consider this differential equation, you see this coefficient is non-zero. So x equals to 0, here x equals to 0 should be called an ordinary point because this coefficient is non-zero. So corresponding to this differential equation, x equals to 0 is an ordinary point. Okay. And corresponding to this differential equation, you see x equals to plus 1 as well as x equals to minus 1 will be called singular points. You see, because this coefficient becomes 0 at x equals to 1 and x equals to minus 1. Okay, so here we can observe the singular points as well as the ordinary points. Okay, now you see this differential equation. We consider this differential equation where P0x, P1x, P2x, all these are polynomials in x. Okay, now x equals to x0, consider this as a singular point of this differential equation. Just we consider this x equals to x0 is a singular point, okay, of this differential equation. Okay, then you see, if x equals to x0 is a singular point, that means P0x becomes 0 at x equals to x0. P0x must be 0 at x equals to x0. Okay, and so if x equals to x0 is a singular point, then this coefficient becomes 0. And also you can say that x minus x0 is a factor of P0x. X minus x0 is a factor of this polynomial because P0 x0 equals to 0. X0 being a singular point, then P0x must be a factor of this. X minus x0 must be a factor of P0x. Okay. X minus x0 is a factor of P0x. I think no doubt about it, right? Because P0x becomes 0 at x equals
Yes,
to.
ma'am.
Okay. Now we divide the whole equation by P0x. Just we divide the whole equation number 2 by x minus x0. Then it should be of the form d2y dx2 plus p1x divided by p0x dy dx plus p2x divided by x p0x into y equals to 0. And then px is actually p1x by p0x. Just we assume qx equals to p2x by p0x. Just we assume. We just make this coefficient 1, and so we are to divide the whole equation by p0x, and so that this coefficient p1x by p0x is denoted by px, and also P2x divided by P0x is denoted by Qx. Okay. Then x equals to x0, which is a singular point, and here px, qx, these are all rational functions of x, because px means actually p1x by p0x, and qx is actually p2x by p0x. Okay. Okay. Now you observe these lines. It is an important line. At least one of px and qx or both have a denominator involving the factor x minus x0. Already it is observed. Px means p1x by p0x, and p2x by p0x is denoted by qx. So it is very clear, because p0x should contain the factor x minus x0. So here at least one of px and qx or both have a denominator involving the factor x minus x0, because it is included in p0x, and we have divided the whole equation by p0x, and here px is actually p1x by p0x, and p0 should contain the factor x minus x0. So at least px or qx or both have a denominator involving the factor x minus x. Okay. Now we just assume this, that both px and qx both have been so reduced that for each the numerator and denominator contain no common factor. Okay, there is no common factor between p1x and p0x, and also p2x by p0x. Just we assume here that px and qx have been so reduced that for each the numerator and denominator contain no common factor. Okay. Now you see what is called a regular singular point. X equals to x0, which is a singular point, if you observe that denominator of px means actually it is p1x by p0x. Okay, so it is actually p0x. Denominator of px is actually p0x, and denominator of qx is actually p0x. But we have assumed here that both px and qx, both these have been so reduced that there is no common factor between numerator and denominator. Okay. Now you see this an important line. If the denominator of px does not contain the factor x minus x0 to a power higher than 1, and if the denominator of qx does not contain the factor x minus x0 to a power higher than 2, then x equals to x0 is called a regular singular point. What does it mean? That means if you observe that the denominator of px, that means actually p0x, denominator of px is actually p0x. If this denominator contains a factor x minus x0 which is less than or equal to 1, you see, does not contain a factor x minus x0 to a power higher than 1. That means what exists here? Here you will observe that the power of x minus x0 should be less than or equal to 1. Similarly, the denominator of x0, the denominator of qx does not contain the factor x minus x0 to a power higher than 2. Then what will happen here? That is, denominator of qx should contain the factor x minus x0 to a power which is less than or equal to 2. Then we say x equals to x0 is a regular singular point. If x equals to x0 is not a regular singular point, then it is called an irregular singular point. Just you observe this example, then it will be clear to understand. You see, x equals to 0, x equals to 1, x equals to minus 3, all these are singular points because this coefficient of highest order derivative, which is, you see, second order derivative, is the highest order derivative involved in this equation, and its coefficient, yes, vanishes at the point 0, 1, minus 3. So all these are singular points, no doubt about it. Now in the next step, to find out the regular singular point, what we have to do? We have to divide the whole equation by this coefficient. So you see, this becomes, you see, if we divide the whole equation by this P0x, then what we get? d2y dx2 plus x square divided by this minus this coefficient divided by this, and you see, just cancelling this common factor, what we get? This is actually px, and again you see qx means this. Now you see, the x equals to, what is the status of x equals to 0? You see, in this denominator, x equals, you see, if we consider this factor x, here, you see, x to the power 0 is here. So the degree of x, the power of x is less than or equal to 1. And here you see, the power of x is less than or equal to 2. So x equals to, yes, since this factor here in the denominator, you may write in the denominator x to the power 0, and in this case the denominator is x to the power 1. So this power of x is less than or equal to 1, and this power of x is less than or equal to 2. So both these conditions are satisfied, which is required for a regular singular point. So x equals to 0 here is a regular singular point. Now if you consider 1, you see, this degree of this factor x minus 1 is not less than or equal to 1, it is greater than 1. So the first condition is violated. You see, you see, if the denominator of px does not contain the factor x minus x0 to a power higher than 1, this condition is satisfied. Okay, this x minus x0, power of x minus x0 should be less than or equal to 1. It cannot contain a factor x minus whose degree is greater than 1. So if we observe here, this degree of this factor or power of this factor x minus 1 is greater than 1, then first condition is violated, and so x equals to 1 is not a regular singular point. What about x plus 3? You see, here the degree of x plus 3 is less than or equal to 1. The first condition is satisfied. Again, in the denominator of qx, you observe the degree of x plus 3 is less than or equal to 2. I think it will be clear to remember in this way that the power of x minus x0 should be less than or equal to 1. It does not contain the factor x minus x0 to a power higher than 1. That means it contains the factor x minus x0 to a power which is less than or equal to 1. Similarly, the denominator of qx does not contain the factor x minus x0 to a power higher than 2. That means you just read it in this way: the denominator of qx contains the factor x minus x0 to a power which is less than or equal to 2. In this case, we say x equals to 0 is a regular singular point. And if it is not a regular singular point, then it is called an irregular singular point. Okay, so here you see x equals, you see, if we consider this factor x plus 3 in the denominator of px, this power raised to the power 1, and here also this power is raised to the power 1. So this power of x plus 3 is less than or equal to 1, and this power of x plus 3 is less than or equal to 2. So both the conditions are satisfied. So x equals to minus 3 is again a regular singular point. X equals to 0 is also a regular singular point, because we can consider here in the denominator of px x to the power 0, and here in the denominator of qx x to the power 1. So this degree is less than or equal to 1, and here x to the power 0 with degree is less than or this is less than or equal to 1, and this x to the power 1 which is less than or equal to 2. So in both this px and qx, you have observed that x equals to 0 is a regular singular point, and x equals to minus 3 is also regular singular point. But x equals to 1, since this power is not less than or equal to 1, is satisfied. So x equals to 1. Whatever be this power, if one condition is not satisfied, then other may or may not be satisfied, but the conclusion is this: x equals to 1 is not a regular singular point. Is it clear?
Yes, ma'am.
Yes, ma'am.
Now now you see the problem, how to solve this type of problems. Okay, you see, solve this differential equation. You see the coefficients. Yes, this is variable coefficients, and order of the differential equation is 2. You have to solve this equation in powers of x. That means you need series solution. Okay, just you write the solution in this form. You see, this is a series in powers of x. X equals to 0 is an ordinary point. The series solution may be assumed in this way. Now you see, if we assume y equals to this, and we need y dy dx and then d2y dx2. So we have to compute first order derivative, second order derivative, and substitute these values here in the differential equation. So you see, just compute dy dx. You see, c1 plus 2c2x, 3c3x squared, 4c4x to the power 3, like this, and so on. Okay, and derivative of cn x to the power n is this, n minus 1. You see, n cn x to the power n minus 1. And I have written the just preceding term is this. Okay, they can calculate d2y dx2. Again, differentiate dy dx with respect to x and obtain this d2y dx2. Okay, and then what you have to do, just you put these values in this differential equation, original differential equation. Just you have put the values of this dy dx, d2y dx2 and y like this. Okay, this is actually d2y dx2, and then you see minus x squared dy dx, so it is dy dx. Okay, okay, minus x squared dy dx, and then it is minus y means this, y means this, minus y means this. Okay, now you see 2c2 minus c0. Just you see the coefficient, actually it is constant term 2c2. First of all, you see which are constant. 2c2 here is a constant, and then c0 is a constant. So combine these two terms. Then you just collect the terms containing x. Here it is 6c3, and you see containing x. Okay, minus c1. This is the term containing x only. So this is the coefficient of x. Similarly, x square. This is the term containing x square. Again, you see minus c1 x square. There is another term containing x square, and here minus c2, another term containing x square. So we combine all the terms containing x square like this. Similarly, x cube, you see here in the first expression 20c5 is the coefficient of x cube. In the second expression, you see minus x cube. Okay, so here x square into x. Okay, minus 2c2, that is x cube, minus 2c2, minus 2c2 x cube. Okay, and in the last expression, you see minus c3 is the coefficient of x cube, like this. And you see the coefficient of x to the power, what is most important, coefficient of x to the power, and how to get this. From the first expression, you see this is the term containing x to the power n. So coefficient should be this. Okay. And in the second term, you see x square should be multiplied by x to the power n minus 2 to obtain x to the power n. So it is minus n minus 1 c n minus 1, like this. And the term containing x to the power n is this here. So it is minus cn. So you collect all the terms. Yes, all the terms. Collect all the terms containing x to the power n. Okay. Now equating to 0, the coefficients of various powers of x. What we get? You see, these are actually constant term. This is coefficient of x. This is coefficient of x squared, like this. And this is the coefficient of x to the power n. Just we have collected the coefficients of like powers of x. And so we get this. Then equate the coefficients of various powers of x to 0 because the right side is 0. So each of these coefficients must be equated to 0 because the right side is 0. So this 2c2 minus c0 equals to 0, c3 minus c1 equals to 0, like 2f(c4) minus c1 minus c2 equals to 0. All these terms should be equated to 0 like this. Now you see, in the first, you see here, c2 equals to this, half c0. Here you see C3 equals to this 1, 6, C1, C4 is this. So C2, C3, C4, you see, we have computed. Similarly, from this, you can calculate Cn plus 2, Cn plus 2 in terms of Cn minus 1 and Cn like this. Okay, Cn plus 2 has been expressed in terms of Cn minus 1 and Cn like this. Okay, so solution in the form of the series is given by this. Just to put the values of the coefficients, you see we have assumed the solution in this form: y equals to c0 plus c1x plus c2x squared plus c3x cubed plus this. So we just put the values of this, you see c2, c3, c4, etc. c2, c3, c4, all these should be, the values of all these coefficients should be substituted and obtain this solution in the form of series. And then you see the terms containing C0 will be separated, and also the terms containing C1 will be separated like this. This is the required solution. If we write the series in this form like this, y equals to C0 plus C1x plus C2x square plus C3x cube like this, but you may write this series in summation form like this, then what will be? You may use any method, but if we assume the solution in this form, just like this, in notation, just if we use this sigma notation, summation notation, then we can use this notation also to solve this series. To solve this problem in the form of series, you may also use this notation also to solve this type of problems in the form of series. Then dy dx should be given by this. Okay, and varies from 1 to infinity. Then you calculate d2i dx to same as before, we have computed, you see, dy dx, d2i dx2, because actually all these are required to substitute this d2i dx2, dy dx y. So we need these calculations and then substitute in this equation, in this given equation, we substitute the values of dy dx, d2i dx2, etc., etc. Okay, then what we get, you see, we obtain this. Okay, you see, you obtain this. Actually, if you put here n equals to 1 or 0, then actually this term will vanish. Okay, so you see n starts from 2 to infinity. And also you see here, you actually divide dx where n starts from 1 to infinity, d2i dx where n starts from 2 to infinity, like this. So finally we combine this. Just we put the values of dy dx, d2i dx2, and then we obtain this. Okay, and then we combine these two terms. We combine these two terms. Then what we get? N is, you see, this is 3n plus 3 into an x to the power n, an x to the power n, an x to the power n. Okay, this is 3n plus 3, an x to the power n. Okay, just you see, 3n plus 3 into an x to the power n. Now we rewrite the second series, just this series, so that the power of x is n minus 2. Okay, power of x is n minus 2, because this term, you see, this term contains x to the power n minus 2. So we just reduce this term having the same power, that is n minus 2. So we just replace n by n minus 2. Just you see, if you replace n by n but dash minus 2, then what we get? You just replace n by n dash minus 2, n by n dash minus 2, n by n dash minus 2. Then after simplification, it will be like this. So we may replace this by this. Just replace this. Okay, just replace this to make this term containing x to the power n minus 2. Actually, here you see this term has been replaced by this. Okay, so that the power of x is n minus 2. And how to get it, that calculation has been done here. Okay, that calculation has been done here. So, after that, we will obtain this, where the summation n equals to 2 to infinity, and then it will be 0. Now, you see, this is a solution. This is a solution of this differential equation. Okay, and you see the right side is 0. So, this coefficient must be 0, like this, where you see n varies from 2 to infinity. So, n is greater than or equal to 2. Okay, this is the recurrence relation for the coefficient an. Okay, now you just simplify this and then express an in terms of an minus 2, like this. And now you see n varies from 2 to infinity. That means n is greater than or equal to 2. So what will you do? N equals to 2, 3, 4, 5, 6, etc., etc. Just to put the values which are greater than or equal to 2. Then you obtain this. A2 equals to this, A3 equals to A4, A5, etc., etc. Then what will you do? Just you multiply all this, or multiply all these elements on the left. Similarly, we multiply all these elements on the left and also on the right. Then what we get, you see, on the left it will be A2 into A4 into A6 into up to A2k, and on the right this minus 3 by 2 into A0 minus 3 by 4 A2, like this. So finally you see you will get this, and after that you see A2 A4 A6 up to A2k minus 2 will be cancelled from both sides, and then you will get this A2k equals to this. Okay, just to simplify this. Similarly, by multiplying all this, what we get? We will get this A3, A5, A6, sorry, A3, A5, A7 up to A2k plus, right side is this. And after cancelling all these factors starting from A3 up to A2k minus 1, we will obtain this. Just you see. So A2k plus 1 equals to this, where k is greater than or equal to 1. Then we put the values of these coefficients in the original summation. That means we put these values here, and then you will get this. You'll see, you will get this A0x, and then you will put the expansions here. After that, you put the values of A2k and A2k plus 1. Already we have computed A2k plus 1 and also A2k. Just you put these values here and obtain this solution in this form. That means if we use the summation symbol, then the calculation should look like this. And this is the last question. I think it is same as before, only there you have to take some substitution. That means you solve this equation in a series about the ordinary point x equals to 1. In this case, what you have to do, just you put x minus 1 equals to v, then you just differentiate dy dx. Okay, dy dx means actually here dy dv dv dx, and dv dx is 1, dv dx is 1, so dy dx becomes dy dv. Similarly, calculate d2i dx2, then you just put these values in the original differential equation here, and then you obtain this. Here just you see x is replaced by v, and the problem now becomes same as before. Just x is replaced by v, no, otherwise the other things remain unchanged. Independent variable x is replaced by v only. Now here v is equals to 0 is an ordinary point, and then we just use the previous method. That means we use this sigma notation. If we use the sigma notation, the series should look like this, and then compute dy dv, then d2i dv2, and put these values here, and then just the process will be repeated same as before. Just continue this same thing what I have done in the second problem. Okay, and finally you have to replace v by x minus 1, and then the solution looks like this. Okay, am I audible?
Yes, ma'am.
Yes, ma'am.
Okay, then stop sharing. Actually, problem number 2 and 3, almost same, only there is some transformation. Initially, just you use the transformation, x minus 1 equals to v, say. After that, it will become same as problem number 2. Just you have to use some transformation here, that is x minus 1 equals to v, and then the problem becomes this, which is same as equation problem number 2. And we have used here the summation symbol, and if you don't like this symbol, then you have to solve this equation just by using the method what I have used in problem number 1. You think of this, which you will apply, which method. Either you may use summation symbols, or you may just write down the series in just a minute. You may write down the series explicitly, and then you can compute the dy dx, dy dx, etc., etc. Then put the values here, and then you just follow this method. Okay, you just decide what will you do. Okay, thank you.
Thank you, ma'am.
Okay, okay,
Thank you, ma'am.
Mark my attendance, ma'am.
okay, thank you.
Excuse me, ma'am.
Tell me.
Can you mark my attendance, ma'am? I am joining late.
56, IT 56.
Yes, ma'am.
Ma'am,
Oh,
can you also take my
Ma'am,
attendance? I also joined late, ma'am.
just a minute.
Suman Kumar, ma'am.
IT
CSB.
56, then IT, then Shuman Kumar.
Yes,
Computer
ma'am.
science 61. Okay.
Hello,
Yes,
madam.
Computer science 61. Okay. And then any more, please? Be
Ma'am,
quick.
ma'am, Sibyl 80.
Civil 80. Okay. Any more? Okay. Okay.
Ma'am, please send this course material.
Yes, I will send it. Don't
Okay, ma'am.
worry, I will send it. Okay. Okay. I must send it as early as possible. Okay. Thank you. May I leave now?
Yes, ma'am. Thank you, ma'am.
Yes, ma'am.
Oh,
Thank you, ma'am.
okay.